15. The Spinning Dancer. The spinning dancer illusion was created in 2003 by a Japanese designer named Nobuyuki Kayahara, and it's a perfect example of how we interpret imagery without any context. The test is made up of a silhouette of a ballerina spinning around in circles, but because all we see is the shadow, it's impossible to know for certain which direction she is moving. To allow us to understand what we're looking at, our brains fill in the missing information and decide for us which way we'll perceive the ballerina moving. But if you make an effort to change the direction of the movement, you'll suddenly be able to see it that way too. In this video, the effect is shown more clearly by the addition of a ballerina on either side of the silhouette, with some of her body parts highlighted. You'll notice that if you focus on the one on the left, then the one in the center will move in the same direction, but it'll switch direction if you instead focus on the ballerina on the right. To make things even more bizarre, if you were to place a mirror next to the silhouette image, the reflected version that you see will actually still move in the same direction as the original, as opposed to the opposite one. Number 14. Ninio's Extinction Illusion. Take a look at this image and count how many black dots you can see where the lines intersect. As you look around, you'll probably be able to see that there are 12 in total, but something strange happens. As you change the direction of your focus, the dots in your peripheral vision seem to disappear. There's no trick going on here, and all 12 dots are present at all times. What you're experiencing is an effect known as Ninio's Extinction Illusion. It was first shown by a French scientist called Jacques Ninio, and it shows what happens when the brain is presented with too much information to analyze. Only a small percentage of people are able to see all 12 dots at the same time, and the rest of us simply see a few of them in clusters. The effect is caused because of the complexity of the crisscrossed lines. It means that the receptors within your eyes are being stimulated and influenced by the activity of nearby receptors, and each individual one starts having difficulties seeing the dots because of the activity of the others. The frightening thing about this is that while it's clear to see what's happening in an image like this, you can only imagine what you're unable to see in the real world because of the same phenomena. Number 13. The McCullough Effect. Discovered by and named after the American psychologist Celeste McCullough in 1965, this next visual illusion comes with a health warning, because if you look at it for too long, it can affect your sense of vision for long periods of time, and may even take several months before things revert to normal. The idea behind it is that you stimulate and train the receptors in your eyes to see specific colors, so that even when the colors are no longer present, you still see them. The example in this experiment is first a screen of horizontal grating that's red, and then secondly, a screen of vertical grating that's green. For the effect to really take hold, you need to take a look at the images alternately for several minutes, and then look at a black and white version of each one. Sure enough, when you do, you'll see green coloring on the monochrome vertical lines and a pink coloration on the monochrome horizontal lines. This again is an example of the shortcuts that our eyes and brains make in interpreting the world around us, and even just looking at the images for a few minutes will result in the effect lasting for an hour or more. Number 12. The Intertwining Illusion. When you first look at this image, it's quite clear what type of pattern you're looking at, isn't it? The vast majority of people see this as a series of boxes arranged in spirals, but look again. Is that really what's there? If you trace your finger around one of the spirals, you'll find that instead of all being connected together, the image is actually made up of concentric rings, and that there aren't any spirals there at all. It's extremely difficult to see them as circles, even when you know that they are, and this is a phenomenon called the intertwining illusion. It's used by researchers to understand the way the visual system works, and it's an example of how, particularly in your peripheral vision, not every bit of information is being fully processed, and you see what your brain expects there to be as opposed to what there actually is. In this case, it's the tilt of the squares that causes the confusion and tricks the brain into thinking that it should be forming a spiral. Actually, what your brain is trying to do is interpret the complex information into what it would expect to find in a 3D space, as opposed to a 2D one, which the image is created in. So it's probably actually trying to understand the image as a tunnel stretching out in front of you. Number 11. The Herring Illusion. This is called the Herring Illusion, and the question being asked here is how straight you think a straight line can truly be. It starts off with two vertical red lines that are parallel to each other, and as you can see, they're both perfectly straight. Things start getting weird though, with the addition of a series of radiating blue lines, and you're left wondering whether the red lines are straight anymore or whether they bulge towards the center. Of course, there's been no change to the red lines, and the curved effect you're seeing is something to do with the way your brain is now perceiving the image. The full process behind this isn't clear, even though the effect was first published in 1861, but it's thought to be related to the way that the parts of our brain responsible for perception tend to expand tight angles and see them wider than they actually are. In this example, the brain expands the angles where the blue lines meet the red ones, and as a result of this, there's no choice but to then see the red lines as a curve. Quite what the benefit to perceiving angles in this way would be is not clear, but it's likely a result of the brain trying to interpret the image in a 3D space as opposed to a 2D one. Number 10. The Zollner illusion. Created by a German astrophysicist called Johann Zollner in the 19th century after looking at patterns in his father's textile factory, the Zollner illusion is another example of how extra elements can trick our brains into thinking that lines aren't straight, even when we know for certain that they are. Here we begin with a series of parallel lines that are drawn diagonally on screen, and then at a series of short lines that bisect the original ones at various angles. Immediately, the longer lines appear to no longer be parallel with one another, and all because our brains begin to struggle to understand the information being presented. This is believed to be another example of how small angles are expanded in our perception, and when this happens, it forces our brain to rectify the rest of the image by making the longer line shift direction. Interestingly, a further study that backs up this hypothesis replaced the long parallel lines with a series of squares, and when the extra elements are added, the squares still appear to be arranged in a straight line, proving that the effect is caused by the interaction of all the lines. Number 9. The checkered shadow. So much of what we see, particularly when it relates to color, is dependent on what our brains expect to see, rather than what we're actually looking at. Take, for example, a chessboard. We all know that these are normally arranged as 64 squares which are alternately black and white. Now, what would happen if, as you see in this image, a large object is placed on the board? As the images show, it casts a shadow over some of the squares. So the question is, what color is the square marked B in relation to the square marked A? Because of the setup of the board, you'll see square A being noticeably darker than square B. But the problem is they're actually both the exact same shade. This illusion was first demonstrated in 1995 by Edward Adelson, who was the professor of vision science at MIT, and shows clearly how our brains alter information to still allow us a contextual understanding of what we're looking at. There's clearly an unconscious decision that recognizing the checkerboard pattern is more important to seeing the scene than registering the color differential being caused by the shadow. And this is an effect that usually will benefit us in the real world to identify shapes and objects. Number 8. Rotating dots. In this clip, it doesn't at first seem like anything strange is happening. Within the larger red circle, there's a circle made up of 8 white dots that are rotating around the larger one, in a similar way to how spirograph toys work. The thing is, when you look closer at what's going on, you'll realize that the white dots aren't actually formed into a circle and are actually moving independently of one another on their own path. If you simply focus on one of the dots, you'll soon see that it's actually moving along a straight line from one edge of the red circle to the other, and then back again. But when you look at the whole image, it's impossible to see the actual motion of the individual dots like this. There's 2 reasons for this. The first is that each dot isn't moving at a linear speed and slows down as it reaches the edge, and speeds up as it approaches the center. The second element is that the combined motion of all them mimics what you'd expect to see if a smaller circle truly was rolling around inside the larger one. So the result is that we perceive the dots as a circle and behave as such. Number 7. The Lilac Chaser. This illusion is known as the Lilac Chaser, or the Pac-Man illusion, and it's a great example of how our perception can show us things that simply don't exist, in a similar way to how you might catch a glimpse of a shadow in your peripheral vision and think it's an actual object of some sort. First, look at what's happening. There's a circle made up of purple dots which, in order, vanish, then reappear again. Instead of seeing flashing spots, however, we immediately perceive the sense of motion and see the blank spot moving around the circle. Now focus on the cross in the center of the image. You're now forcing your peripheral vision to do all of the work, and something strange starts happening. You'll start seeing a green dot moving across the circle, and then as you look for it longer, the purple dots vanish entirely, and all you'll see is a green one moving around in a circle. But how is this possible? This phenomenon is actually the combination of three different effects. The first is called the phi phenomena, where we perceive motion between separate objects that move in succession to each other. The next effect is a result of the way our eyes perceive color, and if you stare at a lilac shape for long enough, it'll leave a residual green one in place once it disappears. The final effect is to do with blurry and non-blurry stimuli, and that eventually the blurry shapes will be ignored in a process called color adaptation. When you see an effect like this in action, how can you ever be sure that something you're looking at is real? Number 6. The Hermann grid. The Hermann grid illusion is first discovered by German physiologist Ludemar Hermann when he was reading one of his textbooks. He noticed that in a grid that has sharply contrasting colors, he began to see things that weren't actually there. Take a look at this image and count how many dots there are in the intersections of the lines. You'll notice that while you see dots in your peripheral vision, when you focus on them, they aren't actually there. In fact, there's not a single dot in any of the intersection points, and no matter how hard you try to focus on them, they'll always vanish. It is an example of what researchers in the field call a simultaneous light contrast, but there's debate whether this is actually an illusion or hallucination. Are we perceiving the intersection points as being gray, in which case it would be an illusion, or are we creating the appearance of non-existent dots, which would be hallucination? Either way, this effect is believed to be caused by an inefficiency within the structure of our eyes that causes latency in how information is sent to our brains to be processed. Essentially, the peripheral view of our eyes is certain that the dots in the intersections exist, and it's only when we fully focus on the area in question that we're capable of seeing it properly without the dot. Number 5. The Kanizsa triangle. How many triangles do you see in this image, which is known as the Kanizsa triangle illusion? Most people answer 2. There's the large white triangle in the center, which is overlaid on top of a secondary triangle with a black outline and 3 circles. Of course, in truth, there's not a single triangle that's been drawn in the image, and we only think there's one because of the visual illusion. What's bizarre about this illusion is the white triangle that we see actually appears to be brighter than the rest of the image, but it's the exact same color, and this is purely down to how our brains are interpreting it. Kinza differentiated between 2 types of functions here that he called the modal and amodal. The perception of the dominant white triangle is the result of the modal completion, whereby you can experience the perception of an object because its edges are seemingly defined by a color boundary, which in this case is provided by the Pac-Man-like circles. As for the second, downward-facing triangle, this is an amodal completion. We don't see it because of the color differential, but because we're already seeing the first triangle. And if it truly is there, then it would be covering up the missing pieces of the one beneath it. The full mechanism behind this process isn't fully understood, but its benefit is clear in the real world. It helps us to differentiate objects and understand what they are, even if we can't see them entirely. And this is a particularly important function when looking at the world in low light conditions. Number 4. The Punzo illusion. First shown in 1913 by Italian psychologist Mario Punzo, the Punzo illusion shows how our perception of size is intrinsically linked with surrounding features, particularly the background. The image is made up of 2 horizontal lines that are parallel with one another, and then the 2 vertical lines that are diverging from one another. The question Punzo asked was which of the 2 horizontal lines is the longest. Virtually every person who sees this image says the top line is noticeably longer than the bottom one, but as you probably guessed, they're actually both identical to one another. The reasons why this works is because our brains have evolved within a 3-dimensional world and sometimes struggle to process 2-dimensional images. The vertical lines frame the image as being in a 3-dimensional space in a similar way to how we'd see a railway track. And because this means we perceive the top line as being further in the distance to the lower one, it must be longer because it still takes up the same visual space. It's this effect that also causes something known as the moon illusion, which is when we see the moon as being larger when it's on the horizon than when it's high in the sky. Rather than being the result of atmospheric magnification like many believe, this is because our brains actually perceive the sky on the horizon to be further away from us than the sky above. So when the moon's the same size in real terms, our brains see it as being much larger. Number 3. The Ames Room Illusion. Invented by an American scientist called Adelbert Ames in 1946, the Ames Room Illusion is an incredibly simple and effective design that makes an entire room into an optical illusion. Visitors are invited to look through a peephole, and what they see on the inside is a room like any other. What's strange, though, is that when someone walks from one side of the room to the other, they either grow to an unbelievably large size or might shrink to become minuscule. Of course, there's no dark magic taking place, and all this is an optical illusion. The room isn't actually a normal shape, and is in fact an irregular hexahedron, which allows for one side of the room to be much farther away from the observer than the other. By using perspective and limiting the angle from which the observer looks at the room, it's possible to make it look normal, while at the same time being completely abnormal, and we actually see things with a similar effect all the time. It's a common trick that's used in movie cinematography to allow for actors to appear a different size to each other. In The Lord of the Rings, for example, an Ames room was used to make the heights of the hobbits look correct in scenes where they were with Gandalf. Number 2. Scintillating Grid Illusion. Similar to the Hermann grid, the scintillating grid is another example of simultaneous lightness contrast illusion. The image that you see is made up of a black background with a series of horizontal and vertical lines that intersect one another, and where each one of them meets, there's a white spot. What's strange about this image is that it virtually shows you the difference between the area of focus and what falls within your peripheral vision. In the circular area you're actively concentrating on, you'll see the image exactly as it is, with the white dots. But as you reach the edge of this region, the dots begin to turn black, and then in your peripheral vision, they don't exist at all. A further effect is that the area you're looking at also seems to be brighter than the rest of the image, although this is obviously not the true case either. Again, all this is to do with the receptive field of your eyes and the prioritized information that's sent to your brain. We are hardwired to look directly at what's most important, such as emerging danger, and everything within its field of view is processed first and more comprehensively. What's seen in the periphery is of secondary importance and is treated as such, meaning that we rarely see it all in its entirety. Number 1. Illusory motion. If you look at this image of patterned circles, it won't take long before you notice the parts of it are moving. The problem is, this is a static image, and every element of movement that you're seeing is all in your mind. It's an effect called illusory motion, and there's lots of different ways in which it can be created. The one that we see most often in our lives is when we watch television. What we're actually seeing is a series of static images being presented to us quickly, and this tricks our brains into believing that we're seeing moving people and objects. In this image, that's completely static. The motion is being created by what's known as peripheral drift illusion. Here, it's all to do with how your peripheral vision is interpreting what's being seen, and you'll notice that the part of the image you're actively concentrating on doesn't actually move at all. While the reasoning isn't fully understood, the main theory is that it's the result of a temporal difference in the processing of luminosity and color in the periphery, and that's because it's interpreted at a different time to the part of the image you're directly looking at. The discrepancies this causes gives the illusion that it's moving.